Okay, the matrix representations of linear transformations. Okay, so before we actually get to this thing, I want to recall one result. So this is something we did in class last time, and maybe I hope you saw it, which is that if you have two linear transformations, if these guys are linear transformations, and you have some basis b1 through bn, the basis of b. Okay. Let me say this. Say that t1 and t2 are linear transformations, and you have a basis of b. If t of b1, t of bi equals, sorry, t1 of bi equals t2 of bi for all I, then what? Then what? Can anybody tell me? If you have two linear transformations and you have a basis, and these two transformations agree on every element of the basis, then something happens. Lizzie?
T1 equals T2?
Then T1 equals T2. Yeah, so then T1 of V equals T2 of V for all V. Okay, so if you agree on a basis, then you agree on every vector. Okay, that is, your linear transformations will be identical. Okay, so that's something we saw last time. If you didn't watch the video, please watch it. Okay. Okay. Second thing I want to recall is given any matrix A from in Rn cross M, then we have a corresponding linear transformation. T sub A, going from Rm to Rn. Right? Everybody remember this guy T sub A? How do you create T? What does T sub A do? Somebody tell me. Dan?
Oh, I wasn't raising my hand, sorry.
No, I was just calling you anyway.
Honestly, I have no idea.
That's all right. That's all right. That's all right. Don't worry. Anybody remember what T sub A is? T sub A? When we first introduced linear transformations? Somebody other than Lizzie? Somebody other than Lizzie? Molly? No, don't remember? Okay, go ahead, Lizzie.
It's when you add a matrix onto the thing you're transforming?
It's left multiplication by the matrix. Okay, so right, we have this guy where T sub A of your vector is just A times your vector, right? Left multiplication. This is, remember this notation? T sub A, it means the transformation you get by left multiplication by the matrix A. Okay, so remember that created a linear transformation, right? Left multiplication by matrix creates a linear transformation. Okay. Okay, so given, I'll say it again, given any matrix, you can create a corresponding linear transformation. Given a matrix, you can create a linear transformation. Okay. In fact, the converse is true. The converse is true. Given any linear transformation, so let me write it like this. The converse is true. Theorem, given any linear transformation from Rn to Rm, there exists a matrix A in Rn cross M, oops, M cross N, sorry. Rm cross N, such that T is left multiplication by that matrix. So what we were saying here is, given a matrix, you can create a linear transformation T sub A. What we're saying here is, given a linear transformation, then there's a matrix that does what that transformation does. Okay, there's a matrix. Your linear transformation actually is left multiplication by some matrix A. Okay, so there's some matrix way of representing your linear transformation. Okay, so everybody actually arises as a matrix. Okay, every linear transformation corresponds to a matrix. Okay, everybody all right? Yeah, you guys are somehow like less. Your class is exceedingly opaque to me somehow. So every transformation actually arises from some matrix, right? Given a matrix, you can make a linear transformation. Given a linear transformation, it actually comes from some matrix, okay? It actually comes from some matrix, right? So, so here's the proof. The proof is by construction, right? We will make the matrix A that makes this happen, okay? So we'll construct A. We'll construct the A that we desire. Okay, and here's how we're going to do it. So let E1 through En denote the standard basis on Rn. Okay, E1 through En is the standard basis on Rn, and let A sub I be T of EI. Okay, T of EI is going to be in Rm, right? Because T maps from Rn to Rm, right? T maps from Rn to Rm, right? And what we'll do is we'll let A be the matrix where these little a's are the columns. Oops. Okay, take a minute and see if you can tell me what T of E1 is. T of E1 equals what? I'm sorry, TA of E1. TA of E1 equals what? Okay. Here's your matrix. Your matrix is this guy, and I want you to left multiply E1 by that matrix. What do you get? Give you 30 seconds. Okay, turn to somebody nearby and say, are you awake? That's okay.
I said it was the first
Okay. Who wants to say what it is? Molly, I'm going to call on you because I heard you say the right answer. What is it?
I said it was the first column of the A matrix.
Exactly. It's the first column of the A matrix, right? It'll be A1, right? right? Because if you take this matrix and you multiply it by 1, 0, 0, 0, 0, what are you going to pick off? What are you going to pick off the first column, right? Right? If you take any matrix A, B, let's just do it for a 2 by 2, and you multiply it by, multiply it by 1, 0, what are you going to pick off? You're going to pick off the first column, right? Right? If I multiply it by 0, 1, I pick off the second column. I multiply by, whatever. If I multiply it by v sub I, I'm going to pick off the ith column, right? For I equals 1 to n. Right? Okay. So we're done. Right? We've found, does everybody see, can anybody explain to me why we're done? Why have we found what we wanted? We wanted a matrix so that T and TA were the same. Okay. We've just found a matrix. TA of EI is AI. TA of EI is AI. Then T and TI are the same. Why? Why? TA of EI is AI for all these guys. Why are T and T sub A the same? Ben?
Because each column vector is the same.
No. No. Read.
Just by like our definition of sameness, like they're the same size and every entry is the same, so they have to be the same.
So, remember how what we're doing? We start off with some linear transformation T. Okay, that linear transformation T doesn't have a matrix associated with it. It's just a linear transformation. Okay, and then we make a matrix. We make a matrix by taking T's action on the standard basis. We put all those guys together. We make a matrix, and then we make this other. We make another linear transformation T sub A. Okay, and I'm saying that those guys are actually the same thing. Right? Why are they the same thing? Lizzie, I think you should be able to answer. No? That's okay. So the hint is,
we have that, I mean, they're,
here's the
the
hint.
entries are this, I mean, the transformations are the same for all I.
Yes. Yeah. So this is it. This is it right here. Okay. This is one. Okay. Over here, remember we did this last time. If two linear transformations agree on a basis, then they're the same linear transformation. Okay. Now we have this guy, T, and T of EI is AI. Right? T of EI is AI by definition. Right? AI was defined to be T of EI. So T of EI is AI for all I. And then here we see that TA of EI is AI for all I. Right? So they agree on the standard basis. Right? T and T sub A agree on the standard basis. So then T equals T sub A because they agree on the standard basis. I equals 1 to n. Okay, so by this fact here, any two linear transformations that agree on the same agree on a basis are the same linear transformation. Okay, so these guys agree, and so they're the same guy. Okay, everybody all right? Everybody all right? Okay, let's go on. Okay, so let's do an example of this. It's an example. It's like a homework problem. Let's define T of x1, x2, x3 as x1 plus x2, x1 plus x2 plus x3. Okay. So what A is such that T sub A and T are the same? What's the matrix representation of this T? So what you do is you say, okay, our proof tells us how to find it. Well, I'll let you think about it. Just think about it for half a minute and see if you can tell me. And if you can't, then that's all right. I wasn't planning to make this a problem, but think. Can anybody tell me what A is? Avery? No? You're just lifting a pen. Yep.
I think it's 1 0 0 and 1 1 0 and 1 1 1.
You're very close. You're very close. Yeah, very close. So just think, how do we make A? We look at T of E1, we look at T of E2, we look at T of E3, whoops, and we put that into a matrix, right? That's what it says here, right? A is the matrix where each column is T of EI, right? Where the ith column is T of EI. Right? That's what it says here. What's A? A is the matrix where the ith column is T of EI. Right? So let's do that. Right? A is going to be rating specific. A is T of E1, right? T of 1 0 0, T of 0 0 1 0, T of 0 0 1. Right? Well, what is that? T of 1 0 0 is going to be what? Nico? T of 1 0 0. So x1 is 1 0 0. So you get
like T of 1 0 0 like that.
yeah, T of 1 0 1 0 0.
It's just x1.
So x1 is 1, right?
Okay.
Yeah, 1 plus, so 1 0 0. Right? It's going to be 1 1 1, right? X1 is 1, so x,
Okay.
right?
Okay.
Right.
So you're multiplying. Is that what's happening?
You're taking T and you're evaluating. You're hitting 1 0 0 with T, right? And here's what T does. T takes x1, x2, x3 to x1 plus x2, x1 plus x2 plus x3, right?
Okay.
So here I'm going to get x1, I'm going to get x1 plus x2, I'm going to get x1 plus x2 plus x3, right? So I get 1 1 1 1 as my first column, right? What about my second column? Well, that's T of 0 1 0, right? So what that's going to be, somebody tell me, Avery?
0 0 1 and then 1
0 1 1, right? And the last guy will be 0 0 1. Okay. Right. So okay. So let's check that T sub A and T actually do the same thing. Okay. So T sub A of x1, x2, x3 is left multiplication by this matrix. Right? x1, x2, x3. And you see what you get, right? You get x1 plus x2, x1 plus x2 plus x3. Okay, so yeah, it does, right? This A was the matrix representation of your linear transformation. Okay, so you see how to find the matrix, right? You just take the action of your linear transformation on each standard basis element, and then use those as the columns of your use those as the columns of your matrix. Okay, let you try one. So so L is the linear transformation. So L goes from R2 to R2, and it reflects each vector across the x-axis, then rotates counterclockwise, sorry, 90 degrees. Okay, so here is a linear transformation. It rotates stuff across the x-axis, right? If you give it this vector, it reflects across the x-axis, right? And then it rotates it 90 degrees. Okay, reflection followed by rotation. Okay, what is T sub A? No, what is A? What is A? If you know what you're doing, this should take you about half a minute at the most. Okay, turn to somebody nearby and tell them what your matrix is. Okay, so right. So what's A? A is going to be T of E1, T of E2, right? T of E1, T of E2. I'm sorry, L of E1, L of E2. Right? How do you get the matrix? Well, you take the matrix's action on each of the elements of the standard basis, right? Okay, so what's L of E1? What's L of E1? You've got E1 here, you reflect it across the x-axis, and then you rotate it 90 degrees. What do you get? You get this, right? So that's 0, 1. Right, okay. And then for the other one, you take L of E2, okay, so you say you take the reflection of that guy across the x-axis, you rotate it 90 degrees, and you get 1, 0. Okay. So the matrix that corresponds to this, the matrix representation of this is going to be 0, 1, 1, 0. Okay. Okay. Everybody all right? Any questions? Any questions? No? Any questions? Okay, so this was the beginning of what would. This is the beginning. this is the beginning. You take a linear transformation, and then you find a matrix that does the same thing as that linear transformation. Okay. And notice that our linear transformation was from Rn to Rm. Okay. Okay. So that was the first step. Now we're going to do something a bit more tricky. Okay, which is, what do you do for abstract vector spaces? What about T from V to W? Okay, not T from Rn to Rn, but T from V to W. Okay. Okay, so this turns out to be a little bit trickier. Okay, so I'm going to write this in the following way. So you've got V and W vector spaces, and you've got T going from V to W, a linear transformation. And we want to represent this T as a base. As a matrix, right? But it doesn't really make sense to talk about T as a matrix, right? Because I suppose that this is, say, Pn, and this is Pn minus 1, and that T is the differentiation operator. Okay. Is there some matrix that you can use to? So I give you a polynomial, and I say, is there a matrix that you can multiply this guy by and get the derivative? That doesn't even make sense at all, right? Because this is not a vector, right? This is not a Euclidean vector. You don't multiply this guy by a matrix, right? What does this mean? 2, 3, 4, 5 times x squared plus x. It just doesn't make any sense at all. Okay, so it's not so straightforward. Okay, but you'll see what we're going to do. So say that V1 through Vn is a basis of V, and F being W1 through Wm is a basis of W. So then there exists a matrix A that's an m by n matrix such that this is the tricky part. Okay, so watch this. A times the coordinate vector of V with respect to the E basis is the coordinate vector of TV with respect to the F basis. Okay, for all V and V. Okay, just write it down. Okay, it may not make any sense right now, but just write it down. And we call this the matrix representation of T with respect to E and F. Okay, so okay, I think the easiest way to make this concrete is to do a concrete example first. Okay, so let's see. Okay, no, actually, let me say, let me give you a picture first to try to get you some sense of what this means. Okay, so there's this matrix, and it has this weird power. Okay, it has this weird quality. Okay, what does this mean? Okay, so here's the picture. So you've got V and W, and you've got your linear transformation going from V to W. Okay. Now, V has a basis, E. W has a basis, F. Right? Okay. Now, every time you have a basis, that gives you the coordinate vector map. Right? So you've got the coordinate vector map going from V to the coordinate vector of V with respect to E. Right? Remember that? I hope you all remember this, right? You've got your abstract vector space, you've got a basis, then you can map from a vector to its coordinate vector. Remember the coefficients that give you the linear combination that allows you to reconstruct this vector. Okay, coordinate vector map. Okay, over here we've got the F basis, right? So over here we also have a coordinate vector map, right? W can get mapped to W sub F. Right? Let me call this coordinate vector map P, and I'm going to call this coordinate vector map Q. Okay, so P is this map going down, P is this map going down here, Q is this map going down over here. Okay, so P is the map from V to W, I'm sorry, V to Rn, where P of V is the coordinate vector with respect to E. And Q is the map from W to Rm, where Q of W is the coordinate vector with respect to F. Okay, so you've got coordinate vector maps. Okay, you've got your two coordinate vector maps. Okay. Okay, so now let's see if we can figure out what this thing says. Here. Okay, this says that if you take a vector and map it through T, and then take its coordinate vector, so is everybody okay with the picture so far? You know, if you're not, feel free to raise your hand. It's okay, it's confusing. I know it's confusing. Anybody confused with the picture? Yes, okay, thanks, Nico, great. Okay, so you've got your linear transformation from from V to W, right? That's okay. We've got our linear transformation. We've got our basis. We've got two bases, right? E is the basis of V, F is the basis of W, right? Okay. Now remember, right, every time you have a basis on an abstract vector space, you've got the coordinate vector map. You remember the coordinate vector map? I hope so, right?
Yeah, like that makes it,
Right, you take your vector, you express it as some linear combination of the VI's, right? And then the coordinate vector map with respect to that basis is going to be the list of coefficients. Okay, so this takes your vector and gives you back a bunch of numbers. Okay, so it's a map from V to Rn. Okay, same thing for W, right? We've got a basis over there, so we've got a coordinate vector map over there too. Okay, that's it. That's all we're saying. Okay. So what is this saying? This says that there exists some mysterious matrix A with a special property. Okay, the property is that if you take any vector in V and you map it through, you take T and you take T of V, so you take your vector, go to T of V over here, and then you map that guy down to TV sub f. You take the coordinate vector of TV. You get the same thing as if you went down first to, so you take your guy V, you go down to coordinate vector with respect to E, and then left multiplied by A. You take that thing and left multiply by A, and you get the same thing. Okay, so what this equality is saying is that there exists a matrix A, so that if you start here and go across and down, or if you start here and go down and across, you can always get the same answer. Okay, that's what this matrix does. Okay, and that's the thing we call the matrix representation. Yeah, Nico.
And then is TV the same thing as W? Like, because you're doing the transformation of V to W?
TV is going to be in W, right? So V is a vector in V, right? TV is somebody in W. Okay, let me do a concrete example, and hopefully that'll bring it down to earth for you guys. So, so here's the example from your textbook. Okay, and so example 5 from your textbook. So you've got V is P3, W is P2, and T from V to W is differentiation. Okay, so you've got your polynomials, right? You've got P3, you've got P2, and you've got the differentiation operator. Okay, and let's let E be the standard polynomial basis 1x x2, F be the standard polynomial basis 1x. So this is the basis of V, basis of W. It's good to have somebody who's brave enough to say that doesn't understand. Yeah, it's very useful because often there are a lot of people who don't understand, but they just don't want to say it. So thank you very much. Yeah. Okay. So just to remind you, if I have something like 2 plus x plus 3x squared, and I take the matrix, take the coordinate vector of that with respect to E, what do I get? What's the coordinate vector of this with respect to the standard basis? Well, I would express this guy in terms of the standard basis, and I take the coefficients, right? Take the coefficients and I write them down. That would just be 2, 1, 3. Right? Right? So this is the map to R3, and there's this corresponding map to R2. Okay. Okay. So, so I'm just going to, I claim that that the matrix 0, 1, 0, 0, 0, 2 is the matrix representation of T. So let's call that thing A, and I'll show you how this works. Okay. 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 Everybody all right? We haven't done anything, so we should be. Okay. So somebody give me a polynomial in P3. Anybody? Zian. Give me a polynomial in P3, please. X squared plus 2x plus 1. Okay, great. Okay, so let's take that guy and go this way, okay, across and down. So when you differentiate it, what do you get? When you differentiate it, well, of course, you get 2x plus 2, right? Okay, and then when you go down to its coordinate vector with respect to this basis, what do you get? What's its coordinate vector with respect to the 1x basis? Russ? 2, 2. Okay, right, that's the coordinate vector. Okay, so this is t x squared plus 2x plus 1, right? Okay, so we get 2, 2 down here, right? Okay, now what happens if we go this way? So what's the coordinate vector? What's the coordinate vector of this with respect to the 1x x squared basis? Stella?
1, 2, 1.
1, 2, 1. Thank you. 1, 2, 1. Right? Okay. And now let's see. Look what happens. If I take 0, 1, 0, 0, 0, 2 times 1, 2, 1, what do I get? I get 2, 2. Right? If I take a times 1, 2, 1, I get 2, 2. Okay, and that will happen with any vector, with any polynomial that I choose. That'll happen with any polynomial that I choose. Okay, and it's in that sense that this A is a representation of differentiation. Okay, this A is differentiation. Okay, this matrix here, you didn't think it looked like differentiation, right? But this matrix is differentiation. Okay. Yeah.
That's only differentiation in P3.
On P3. Yeah. Only on P3. Yeah. And with respect to these bases. Okay. If we change the basis, we get a different matrix. Okay. We change the vector space, we change the basis, right? Things will get more complicated. Okay. 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 So that was a lot to absorb, right? That was a lot to absorb. So the two things that we did today, one, we started off with a map from Rn to Rm, and we said, oh, there's actually a matrix A that does the same thing, right? So that the matrix A, left multiplication by that matrix, does the same thing as your linear transformation. Okay. That was the easy one. Okay. Now what we said, but we haven't justified it at all, okay, is that if you have an abstract linear, if you have a linear transformation between abstract vector spaces, and you have two bases, then there's a matrix that goes across here. There's a matrix A, so that if you go this way or that way, you get the same thing. Okay, and that guy is called the matrix representation of this transformation between abstract vector spaces. Okay, now we haven't said how we make the A, but it's actually pretty similar to what we did. It's actually pretty similar to what we do in the previous one. Those of you who have watched the last video or attended the last class, let me tell you what really happens. Okay. What really happens is this. These maps here, P and Q, are isomorphisms. Okay, that is, they're reversible maps. They're reversible. They're inverse linear transformations. So I actually have a linear transformation going backwards. P inverse. Here. Okay. If I look at this map, this map that goes from Rn to Rm. Okay, if I look at this map going from Rn back through P inverse and then T and then Q, so it goes P inverse and then T, T and then Q, then that's a map from Rn to Rm. Okay, that's a map from Rn to Rm, just like, we had some map from Rn to Rm, and there was some A corresponding to it. Okay. There's an A corresponding to that guy, right? So we actually can think of the first thing we did. There's a matrix such that QTP inverse is left multiplication by that matrix A. That's the A we're looking for. That's actually the A we're looking for. Okay. I'll say it again, if you haven't watched the video or aren't too sure about inverse linear transformations, please watch it. Please watch it. Okay, that's it for today.